The last type of raster analysis I want to discuss is custom analysis, where we can search the toolbox and code sharing sites to find custom scripts, tools, and more to analyze raster data. And if you look on the right side of your screen there, you can see I've searched the ArcGIS code sharing website, and I've located a bunch of raster analysis tools, including IFSAR tools, which are radar, satellite imagery management tools, analyzing the potential impacts of ocean vessel wakes on shorelines, transmission line routing model, a suitability modeler, soil erosion. So if you can imagine it, somebody's probably already done it, and searching the ArcGIS code sharing is a good resource. Also, the geoprocessing toolbox includes a bunch of functionality as well. You can see some of those listed on your screen there, including mosaic data sets or ortho mapping and custom hydrology or solar radiation tools. Now, in the next few slides, we're going to focus on custom surface analysis, where we're generating analytical surfaces from digital elevation models to analyze a site. What are elevation surfaces? They're surfaces with or derived from elevation values. And we typically start with a digital elevation model that stores the elevation as the cell value. And that Z value includes the vertical coordinate, so the elevation. And it's important to note that the Z is not always the same unit as the X and Y values. You'd like it to be, but I have run across raster digital elevation models where the X and Y values were in feet and the Z values were in meters. So it's important to check that before you start performing your analysis and generating analytical surfaces from a DEM. Now, what type of surfaces do we derive from a DEM? Hillshades, contours, slope, aspect, and viewshed are an example of a few. And you can find the tools required to generate these surfaces in the Spatial Analyst Tools toolbox in the Surface Tool set in ArcGIS Pro. First, let's talk about the Hillshade Geoprocessing tool, which simulates a sunlit landscape by setting the compass direction, known as the azimuth, and the distance above the horizon, known as the altitude, of the sun, which is the illumination source for our digital elevation model. And if you look at the example on the right, you can see I have my illuminated elevation raster source in which the sun is placed in the northwest sky at 315 degrees and at 45 degrees. And then it illuminates each cell based on the cell's relative orientation, which is slope and aspect, to the illumination source. And in this example right here, the darkest colors represent the areas that are in shade, and the lightest colors represent the surfaces that are really lit up by the sun. Now, those parameters of a 315-degree azimuth and a 45 degrees above the horizon are important because we utilize those exact parameters to generate a cartographic hillshade, which is created by placing the illumination source in the northwest quadrant of a map. And this is a technique for visualizing a three-dimensional surface in a two-dimensional display. If you look at the images on the right, and I believe this is Mount St. Helens before the famous eruption in 1980, you can see that the cartographic hillshade is illuminated from the sun being placed at 315 degrees or in the northwest corner, and it illuminates the northwest slope, and the southeast slope of the mountain is in shadow. And so by placing the sun in this northwest corner, it creates an optical illusion. Even though this is a 2D image, it looks three-dimensional on this page. Now, in addition to cartographic hillshades, we create analytic hillshades by placing the illumination source in support of a specific analysis, not just to illuminate the surface from the northwest corner. And so what type of analysis might that be? You could, for example, be looking at the potential of a snowpack to have an avalanche, or you could be trying to see how long a side of a mountain is lit up by the sun for a coffee plantation that you're planting there. And you can use a solar calculator to figure out what the azimuth and what the sun angle is depending on your location and the time of the year and the time of the day. And I've got a link right there for the NOAA solar position calculator that you can use to do that. Now, as a general rule, we always use cartographic hillshades unless we're performing a specific analysis where we want to place the sun in some other location besides the northwest corner of our hillshade. We also use digital elevation models and the contours geoprocessing tools to connect points of equal values with lines. These are generally known as ISO lines, and more specifically as ISO bars that connect points of equal barometric pressure, isohyets that connect points of equal rainfall, isotherms connect points of equal temperature, for example. And these ISO lines or contours reveal the rate of change across an area for continuous data. The closer the lines are together, the more rapid the change in values. The terms contours and isolines are used interchangeably, but in GIS, if somebody says contours, they're typically referring to elevation. If you look at the example on the right, you can see I've got my raster with my elevations of different colors, and the contour lines are connecting the points of equal elevation. We use the slope geoprocessing tool and a digital elevation model to calculate the incline or steepness of a surface. And that can be expressed as degrees or percentages. If you look at the image on the right, you can see I've got that colored raster in which the reds represent the steeper slope and the greens represent the flatter slope. And you can see in the legend that the same slope can be expressed in degrees or percentages, depending on what you're trying to accomplish and who your audience is. Now, you calculate the percent slope by dividing the elevation difference by the distance, or what we like to refer to as rise over run. And technically, it's rise over or divided by run times 100 equals the percent slope. And in the example on the right, 150 divided by 300 is 0.5 times 100 equals a 50% slope. Now, calculating the degree of slope is a little more difficult. You need to take the arc of the tangent between the rise and the run, and this can be between 0 and 90 degrees. So 0 would be completely flat, and 90 degrees would be a vertical cliff. You can use a digital elevation model and the aspect geoprocessing tool to calculate the orientation or compass direction of slope. And that is where you're identifying the downslope direction of a raster cell to its neighbors. And you can imagine if you're standing on a slope and your chest is facing downhill, that is your aspect. And it's measured clockwise in degrees from 0 to 360. And so if you look at the example in the upper right-hand corner, you can see north is 0 or red in this example. East is 90 or yellow. South is 180 or green. And west is 270 or blue. And flat areas are typically assigned an aspect of -1 and symbolized as gray. If you look at the example in your lower right-hand corner, you can see that we've taken two DEMs for Mount St. Helens, one before and one after the eruption, and used the aspect geoprocessing tool to see how it radically altered the aspect or the direction that the slope faced around Mount St. Helens. The last surface geoprocessing tool that I want to discuss is ViewShed, which is the area visible to the human eye from a fixed vantage point. And we can use the ViewShed geoprocessing tool to identify the cells in an input digital elevation model raster that can be seen from one or more observation points or lines. Each cell in the output raster receives a value indicating how many observer points are visible. So in a view shed where there's just one observer point, each cell is assigned a 1 for visible or a 0 for not visible. And if you look at the example on the right, you can see I've got my observer point, I've got my input raster DEM, and I calculate the output viewshed raster. And all the cells that are green are assigned a 1 and are visible to the observer, and all the cells that are red are assigned a 0 and are not visible to the observer. And there are many applications for the ViewShed geoprocessing tool, from calculating what it might look like from a scenic overlook to identify vantage points for the Secret Service to protect a presidential motorcade that's winding through an urban downtown. Now we can use these various surface analysis geoprocessing tools to perform a higher level visibility analysis, where we can determine what an observer sees from any given location. And we can use visibility analysis to answer questions like, what is the best location for a scenic overlook? Is the proposed cell tower visible from the park road? And will the solar farm be negatively impacted by shadows? And we can use our analytical process, question, inform, analyze, decide, and present to develop a visibility analysis process. For example, first answering the question, view what from where, then informing your analysis by identifying the observer, target, and terrain. Now we perform our analysis by performing linear or radial line of sight analysis. We need to decide what our findings are telling us and refine our analysis. And last, we present our analysis by quantifying and visualizing visibility. At this point, you should be able to differentiate between Euclidean and cost distance. Euclidean is the shortest distance and doesn't take any impedance into account. Cost distance is the cheapest distance and it takes impedance into account. You should be able to explain how cost is used to perform raster path analysis, including generating a cost surface, a cost distance, a cost back link, and use those input rasters to create an optimal path raster or an optimal path line. You should be able to list analytical products you can create from a digital elevation model, including hillshades, contours, slope, aspect, and viewshed. And in the lecture demonstration and the Onion Creek Trail suitability analysis, you should create analytical surfaces from a DEM and perform a least cost path analysis.